students. Today we are going to discuss about another very important property of fluid, which is called viscosity. So in simple word, the term viscosity refers to a frictional or resistive force which acts between the two consecutive particles of a fluid or a liquid. So viscosity is the resistive force or frictional force offered by the particle of a fluid. So if two consecutive particles of fluid, one is in rest and another is having a downward motion, then in between these two molecules, the contact surface, it will act a force in the upward direction, that opposes the motion of the particle of the liquid. That upward direction resistive force is called here viscosity. The viscous force is the frictional or resistive force offered by a particle of a fluid. So, considering a flow of fluid through a cylindrical pipe, we can divide the flow of liquid in some consecutive layers, and it is assumed that the movement of the liquid is due to the slipiness of a layer of liquid one over another. One layer, it will slip like this over another layer in case of a normal flow, and we assume here that this is not in the case of turbulent flow. This is a theoretical and 100% laminar flow. Okay. So now the viscosity, it depends on two things. One is the area of the surface of contact and another is the velocity gradient. What is velocity gradient? Suppose a layer, it has a layer of liquid, it has a velocity v, and just over the layer of the liquid at a distance of dz, we found that the velocity changes to v plus dv. So what is the change of velocity? That is dv. And what is the change of the thickness of the liquid layer? This is dz. So change of velocity with respect to the change of the thickness is called velocity gradient. So velocity gradient is termed as dv, that is change of velocity, by dz, that is change of thickness. So if v, that is viscous force, this is directly proportional with the area of contact, and also it is directly proportional with that velocity gradient. Now if you combine these two, then we will get the viscous force is directly proportional with A area into dv dz, that is velocity gradient. And the minus sign, it is very important, which indicates that viscous force always acts opposite to the motion of the fluid. So if you have to change this proportional sign into equal sign, so it will come that f is equal to some constant mu minus some constant mu into A into dv dz. That constant mu is called coefficient of viscosity. So mu is called coefficient of viscosity. What is the unit of mu? Unit of mu is poise. That one poise, if we consider here the unit, that mu is equal to f by A into dz dv. We are putting the values of the units of force, area, dz and dv. We are getting that the unit of mu is Newton meter to the power minus 2 into times second. So Newton second into meter to the power minus 2. And if we do the dimension, it will come, the dimension of coefficient of viscosity, it will come m L to the power minus 1 into T to the power minus 1. And the most useful unit for coefficient of viscosity is called poise, and 1 poise is approximately equal to 0.1 Newton second per meter square. Now, some liquid, it follows this law. This law, if viscous force Fv is equal to minus mu A dV dz, this law is called Newton's law of viscosity. Some fluid, it will follow that Newton's law of viscosity. They are called Newtonian fluid. And some of them does not follow that law. They are called non-Newtonian fluid. That means Newtonian fluid, in case of Newtonian fluid, the stress, it is a simple factor of dV dz. It is a simple factor of dV by dz. In that case, that tensile stress versus dV dz plot, we will get this straight line passing through the origin. This is number 1 liquid. Tau tensile stress is equal to mu dV dz. So this liquid is called Newtonian fluid. Whereas in some other cases, that tensile stress tau does not linearly varies with dV dz. That in those cases, tau is equal to mu dV dz whole to the power m. The m is more than 1, that m is greater than 1. These cases, in that case, the graph of tensile stress to velocity gradient will look like a parabolic curve. That fluid are called non-Newtonian fluid. In some fluid, the graph or the graphical representation of tensile stress with dV dz, it will look like this. That means it is a straight line, but it will not pass through origin. In that case, those fluids are called plastic fluids. And in some other cases of fluid, the curve of tau versus dV dz, it looks like this. Number 4. Those are called thyrotrophic fluid. Okay. Now, this viscosity, there are 2 factors on which the viscosity depends. Number 1 is temperature. Very important factor. In maximum cases, if the temperature increases, then viscosity decreases. If we took a very simple example, ice cream, it is more viscous than milk. If you melt the ice cream, then it will convert it into milk. So milk, the temperature of milk is more than that of ice cream. That is why milk is less viscous than ice cream. And moreover, the effect of pressure, it does not have any effect of pressure. That pressure, change of pressure does not affect on the viscosity of a liquid. This viscosity mu, it is also called absolute viscosity, and the ratio of that absolute viscosity to the mass density is called kinematic viscosity. So nu is equal to absolute viscosity mu by mass density rho. Now what is mass density? Specific weight by gravity. So it will come that kinematic viscosity will be mu g by gamma. So the unit of that kinematic viscosity nu is called Stokes, according to the scientist Stokes, G. Stokes. Okay. Now this viscous fluid will come to the second part of that viscosity topic, that is some laws or equations. The very important law, the first very important law regarding viscosity is Stokes' law. Suppose a condition, it is a container it has some liquid on it with viscosity mu. A small spherical ball with radius r is dropped in that liquid. So it will come down due to the weight of the ball. And after some time, when the buoyancy force and the weight of the balls are equal, then the ball starts moving in the liquid, or we can say that it will move with some constant velocity till it reaches the bottom of the container. That constant velocity is called the terminal velocity of the spherical ball. Now, according to Stokes, the viscous force that will act on the spherical ball is given by 6 pi mu r v. That v is the terminal velocity of the spherical ball, and the gravitational force that will act on the spherical ball, it will give the weight of the ball minus buoyancy force. So what is the weight? Weight means mass into g, acceleration due to gravity. And what is mass? Mass is equal to volume into density. So volume into density into g, that will give the weight of the ball, and as well as that volume or the buoyancy force of the ball, that will give like this. As we know that the volume displaced by the ball is equal to the volume of the ball itself. So it will be like this, the buoyancy force. So if we consider like this, so this will be 4 by 3 pi r cube, gamma s minus gamma will be your force due to gravity. So under terminal velocity, these two forces are equal. That is why we can calculate that the terminal velocity v will be 2 by 9 r square by mu into gamma s minus gamma. Gamma s is the specific weight of solid and spherical ball, and gamma is the specific weight of the liquid. Another very important equation of flow regarding viscosity is Poiseuille equation, that is flow through a very narrow tube. Flow through a very narrow tube. Considering the case that the water particle or the liquid particle which is at the top and bottom layer, which is directly in contact with the layer of the tube, are at rest. So their velocity is 0, and the middle of the tube, the velocity is become maximum. So if you plot like this, then it will, the velocity profile will look like this. Velocity profile. Okay, and the factors on which the volume of liquid passes through the tube per unit time is given by K, some constant, into pressure by length, that is the pressure gradient, that is dP by dl, that is the pressure gradient to the power A into viscosity to the power B into radius of the pipe to the power C. By dimensional analysis, we will found the values of A, B, C, and we will get this equation, that volume of liquid flows per unit time through a very small narrow tube will be K value is pi by 8 into pressure into R to the power 4 by mu into L. This is called the Poiseuille equation of the flow through a narrow tube.